That's too much work. And it's depressing. It's depressing, let's be honest, Cody. So, the only way to be 100% confident would be to be certain, as Max said, but what's the only way to be certain about that obesity rate? Measure every element of the population. Impossible, right? Why is that impossible? Think about it. U.S. Say that again. People die and people are born. That's a very generic statement, 28% of U.S. population. That's a hugely vague statement. Is that infants? Does that include infants? Are infants using cell phones and self-reporting their height and weight? I mean, it's a ridiculous question, but at the same time, that's a ridiculous statement that they made, which deserves to be picked apart, I think. So, back to confidence. If confidence isn't certainty, then what is it? If confidence is, now this is different than how we use the word confident in our lives, right? In our lives, when you're confident in something, you know, you're standing behind that. You're like, I know this is right. And then somebody asks you a question, and you might go, okay, I'm pretty sure it's right. And my son, who's going to be 9 in October, has already started to say things like, I'm 98% sure. Like, he knows not to use 100 because things do bite you in the butt sometimes, right? So it's adorable to listen to that. And he changes it. I'm 95. No, I'm 99. No, wait, I'm 98. It's just like, where are you getting those numbers from? It's adorable. I love listening to it. It makes me happy. Hi, Max. He'll be 26 by the time he watches this. You talking about me in class? What the hell, Dad? So what does confidence mean? What does statistical confidence mean? This is a hard question. Keep thinking about it. I'm going to show you something. Do you know what this is? It's okay if you don't. Think back to last class. How did the last class start?
Cards.
With cards. What were we doing with cards? You made a very strong statement a week ago, didn't you?
Yes.
You did.
Yeah.
You made a very strong statement a week ago about a certain deck of cards I brought to your class.
Yeah.
You did, that was the claim! The very strongly worded, you got a stacked deck. Very, 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 very harshly worded statement. So what did I do on Thursday with you all, or what did I have you do Thursday? I wanted you to test that claim, right?
Yeah.
I wanted you to test the claim that I had stacked the deck. How did you do it?
Who's playing?
Yep, I gave you real cards on Tuesday. On Thursday, I took the real cards away and let you use an Excel spreadsheet to simulate a real deck, which was much quicker. Assuming that the deck was 50-50 red and black, the Excel spreadsheet was actually doing that for you. Perfect, good so far? Good so far? Maybe? Okay, good. Each one of these rows is one of you. Now, if you look at those rows, you'll actually see your number somewhere in there. I colored the one red, 152, that's when Max was born, and I got half, so I saw that number. So one of you had 153 successes, and I got all. So, oh, there's another one up there I missed. Look at that. So here is how many times you didn't get black cards in your trials, and this is how many times you ran the experiment. So for that first student, you ran 1,001 trials. In those trials, 34 came back with no red cards. The next student ran it 2,000 times, and they got 60 trials where there were no red cards. 5,970, 184 with no red cards. The number right next to that is the percentage if you divide the first number by the second number. So if you divide 34 by 1,001, you get about 3.4%. 3.4%. Fair enough so far? So in other words, all these percentages are like the obesity rates in that article. They're kind of nice, except for the fact that they're not, because they're incomplete. I want to pull this down a little bit so these line up better. And what I tried to do here was pull it down a nice little bit. Oh, that's too far. I want to line up the orange boxes. Excel's not good at this. I'm trying to make the orange box. Yeah, that's pretty good. I'll stretch the blue line down. So, speaking of these orange boxes, what the hell are these orange boxes? Do you have any idea what the orange boxes up there are?
So I'm guessing the blue is the average.
The blue is the percentage that you should get no red cards if you deal 5 cards out of a deck. It is exactly 3.125, and that's what that blue line is. It's sitting at 3.125%.
It just makes me think of I shouldn't say a reverse bell curve, but it makes me like, that's all of our data in
Oh,
there.
Okay.
Is that not what I'm, is that?
No, you're very close, actually, Katie. You're very, very close. This first orange bar right here, where's 3.4% on that orange bar?
Right here.
Right here? Right in the middle of it. So what's the rest of that orange bar?
The outliers. Or not the outliers, but
Yes, but use a term we've been using today. I applied the margin of error to the 3.4%. Don't worry about how to calculate it right now. We'll get to that next week, I promise. But that's the margin of error attached to the 3.4%. If you had to approximate it, what would you say? It's about 1%? 3.4 is here, this is about 2.4. It's about 1%, maybe 1.1%, something like that.
Yeah.
Don't worry about why. We'll get to that later, I promise. I promise. Soon. Right now, just realize, number one, it has a margin, and number two, I've applied it for you. Is that fair? Is that okay? Okay, good. What do you notice about 3.125%? The number 3.125%, is it in or out of that interval? Is it in that interval or out of it?
In.
It's in, right?
Yes.
That means that even if we didn't know what the true percentage was, it's in that interval. Somewhere, right? Somewhere in, remember the discussion we had earlier about we're not sure where the true percentage is? But it's somewhere in that one. We do know a little bit of fiction, don't we? A little tiny bit of fiction this time. We know a little bit of fiction because we know for a fact it's 3.125%. I'm illustrating with your samples to show you how powerful your sampling was. Ready for the next student? Next student. They got 3%, 60 out of 2,000, 0.03, essentially right there. What's their margin of error? Ish. Ish. If you had to approximate what it is.
0.8.
About 0.8, yeah? 0.8, 0.7, point somewhere in there?
Yeah.
Why is student number 2's margin less than student number 1's?
They have more,
Remember the discussion we had earlier? They ran more trials. Larger sample size. You'll notice a little correlation between larger samples and shorter margins. You'll notice a little correlation between larger samples and shorter margins. That's a mathematical consequence. We'll get, like I said, we'll get into that next week. A little more comprehensive attack on margins. But right now, just realize that every single sample statistic has to have a margin plugged onto it. Did student number 2 catch the parameter we were looking for?
Yes.
Is it in there? It's in there! Did student number 3 catch it?
Yes.
Did student 4?
Yes.
Did student 5?
Yes.
How many students caught it? I don't know. Let's count. 1, 2. You count. I'll count. Smiling.
All except 2.
All except 2! You guys count much quicker than I do. Say that again. Taylor.
There's one kind of in the middle that's right up.
Oh, this one's hard to know. Yeah, this one's tricky. I wanted to make the blue line thick enough to be obvious where it was, but then if I make it too thick, then it actually gets too far to the left and right. It's kind of like hitting a bullseye of the target by throwing a hand grenade at it. Well, the bullseye's gone, right? Yes, so is half the hillside. But okay, so either 2 or 3 caught it. It didn't catch it. So how many did catch it? How many total are there?
28. So 25.
20. If I make it 27 because I'm a bastard, row number 1 actually has the S. So it's 27.
So 24.
So if we do 2 out of 27, or 25 out of 27, what is 25? What percentage of our intervals caught it? What's 25 out of 27? Say that again.
98%.
98%. And if we do 24 out of 27, what do we get?
90.
That's 3 27ths. That's 3. That's 1/9. That's down about 91%, somewhere in there. So we can approximate it somewhere between 91 and 98%, which is right around what percent? 95. Remember the 95% confidence that they talked about
Yes.
in the article? I'm waving my hand right in front of you, I apologize. What does 95% confidence mean? What does it mean? Use the right tense. What does it mean? It means that if lots of statisticians repeat an experiment over and over and over again, 95% of them are going to trap what they're looking for in their confidence interval. 5% of them will not. Let's make sure we write that down, okay? This is important. This is important stuff. Let's put it on that sideboard. I'll turn the lights back on and make sure you wake up. Confidence. Let's put it over here. I think it's worth it. Erasing our old work. And to see what confidence means. What is, and I'm going to put another word in here to make sure we separate it from normal confidence. Like, I'm so confident I can do X. What is statistical confidence? Statistical confidence. At the end of the day, it's a percentage. At the end of the day, it's a percentage. It's a percent of trials that can be expected to capture a parameter inside a, I want to put another term here, confidence interval. .95% confidence is almost always used in research these days. We'll talk about why that's a good / bad / arguable idea.
Is that what you would call the confidence interval?
The confidence interval, thank you. The confidence interval, thanks Jen, is always the same thing. It's a statistic plus or minus the margin of error. That's all that is. Thank you for that question. That's what a confidence interval always is. Statistic plus or minus margin. That's a confidence interval every time, no matter what statistic you're studying. How badass is that? That's pretty badass, I'm not gonna lie to you. No matter what you're studying, are you studying averages? Are you studying proportions? In this class, that's all we're gonna be studying. But we can also study differences of proportions, differences of averages. Guess what you do? You find the statistic you're studying for, and then you add a margin to it, and subtract a margin. That's the entire region is the confidence interval. So all these bad boys up here are your confidence intervals. Look at this bad boy right here. It's so wide. How come? Because that person only ran 378 trials. That's cool. That's totally cool. And that's okay, because guess what? That's one of the ones that actually trap the parameter. See what I'm getting at here, friends? That's one of the ones that actually trap the parameter. Now, of the ones we saw, somewhere between 24 and 25 captured it. It's hard to know with that one right there. I have to go back and look at the actual calculation. But that's damn close to 95%, right? Damn close to 95%. And that's the idea of statistics. A very common percentage used is 95%. All that means is if 100 independent research organizations do the exact same experiment, they're all trying to figure out the rate of relief for this new medication. And 100 experiments are done. 95% of them, on average, are going to figure out what that rate of relief is. The other 5% are going to miss it. They're going to be too high or too low. Just like ours were. How were ours? These were too high. This one's sneaking up on too low. It's hard to tell. But that's what's going to happen in 5% of cases if you are at 95% confidence. What if you're at 90% confidence? What's going to happen then? What percent are going to catch it? Sorry, it's a pretty easy question. I'm sorry, I'm yelling again. 90%? How many are going to miss it? 10%. Why would anybody in their right mind use 90% confidence? Don't answer that question right yet. It's kind of hard to answer right now, actually. We'll come back to it. I promise we'll come back to it. Okay. Does that make sense? Do all those terms make sense?
Yes.
That's what confidence means in statistics. It means the percentage of time you can expect the parameter to be in an interval. Now here's the problem, folks. Here's the problem. It's pretty obvious in looking at these which ones are the oddballs. Like, it's pretty obvious that this one's going to be an oddball because on average the entire thing is to the right of the other ones. Is that when you do research, statistical research, you generally don't get to see all of these. You get to see yours. In other words, Taylor, this is yours. I'm making this up. This is you. This is Taylor. This is all she knows, is her low and her high. And she says, I'm 95% confident that the parameter's in there. She has no way of knowing what the other 19 out of 20 people who have done this report have done unless she publishes her report and makes it part of the conversation. Many people don't make it part of the conversation. They publish it and ignore the conversation, or they don't bother publishing it, which means we're at a loss then to know how it looks when compared to everything else. Does that make sense? Or does it make sense? Okay? So the only way to know it's 95% historically over time is to compare your results to others that are like yours. So this is, I love looking at this, but realize that when you did your, how many of you all looked at your neighbor's work on Thursday when you were doing the F9 thing and the, only a couple of you, look at that, only like 5 of you. How like statisticians we are. You know, and then we don't look around. But the thing about it is, when you look around, you begin to realize stuff like this. And this whole, that's why when you said bell curve earlier, Katie, I loved it. Made me so happy. It's not so much that it's a bell curve. It's that it's the sampling distribution of your guys' results. And then when you look at it like this, it's like, oh, clearly these are off. Clearly. Well, it's only clear because we know that that's 3.125, right? You take that away, it's not as clear anymore. But that doesn't change the fact that 95% is still there. That there are some that missed it. And then it gets more cloudy when you don't realize which one you are in the mix. Who's pissed right now? You're like, what the hell? This class sucks. You never know if you're right or wrong? No, that's the problem. You don't ever know if you're right or wrong. You try to minimize the error with stuff we're going to learn in this class together. Talk to me.
So, okay, going back a little bit.
Yes.
The larger the sample, the smaller the margin.
Smaller the margin. It's going to shrink down like this.
Right, so the smaller the margin, the better, right?
Generally speaking, as long as your data is good, yes. All things else being equal, yes. The answer is yes.
With the data from obesity, with the 175 compared to like 350, how does that sample not relate to each other? Like, why, you said that sample size doesn't matter, but I got the same answer as him.
No, time out 1 second. I didn't say sample size doesn't matter. I said having 2 different sample sizes is okay.
Okay.
You can have the one had 350 and the one had 175, and they're both fine, so long as the data was collected well.
But even though they have different margin of error?
That's okay as long as you use the margins correctly. You would have one would have 0.1, one would have 0.2. But even so, even if I was to make this 0.1, this would still shrink down and be nowhere near the other one, and you can still use it conversationally. Is that fair?
Yeah.
That's a great question. Thank you. Thank you. Wonderful question. Please keep asking questions like that for the next 10 weeks. Everybody, keep them coming, because this is not intuitive stuff. 95% confidence, that's lame, why not be 100%? Keep talking. Why not use 99.999%? There's a good reason. There's a very, very good reason. Some of it's cost. Some of it's other stuff. We'll get to that too. Keep those questions coming. I love them. Okay so far? All right, let's keep going. Let's keep going. Let's keep through these little